Welcome to lecture 25 of Fox. We're going to be talking about context-free grammars or context-free languages, which are very useful for tasks like parsing or compilers, all the kinds of good stuff we like to do with programming languages. Okay, now, before we get going, let's talk a little bit about what we did last time. So last time we introduced this beautiful computing model, basically a very primitive computer, a state transitioning machine, which we call a deterministic finite automaton. So it just transitions states, takes its input, reads the input, as it reads the input, transitions states, and finally rests in some state when the input's done. And if the resting state is a yes state, you say yes, otherwise you say no. So a very simple machine we can implement with a very simple technology, okay, very simple mechanical technology, and it is very powerful. Okay, we saw that DFAs can solve any regular expression, so solve any problem that can be described by a regular expression. So what's a computing problem? It's a yes set. We can describe yes sets in many ways. One way to describe yes sets is using regular expressions. Okay, and for any yes set that can be described by a regular expression, you can construct a DFA to solve that problem, to identify whether or not a string belongs to that yes set. Okay, that's a decision problem. Okay, and you can take finite languages, finite sets, finite yes sets, finite languages, and do all kinds of complicated things to them: complements, unions, intersections, concatenation, clean style. You can do all that, and providing you start with finite languages, a DFA can solve those problems. Okay, so let's see what the workflow was. The workflow is we constructed a model. We built a very simple computer, the DFA. Okay, and we showed how it solves problems. It solves problems by transitioning states, and depending on where it ends up, it says yes or no. And then we analyze this model. Okay, what are its capabilities? Regular expressions, very powerful. And what are its limitations? And that's where we inserted a thorn into our thigh. Okay, we found that the DFA cannot solve so simple a problem as equality. Now, that's not acceptable. Okay? We don't want computers that can't solve so simple problems as equality. Okay? And so this means that we need a new model. We need a more powerful machine. Okay? So, let's go to the board and discuss for at least, for 5 minutes what kind of more powerful machine can solve equality. We'll, in the process, describe what, this problem of equality was. That was the thorn in the DFA's thigh. And then we'll start talking about context-free languages, context-free grammars. Okay, let's talk about this problem, this computing problem, this equality computing problem that is causing the DFA all these headaches. Okay. So equality. So remember, a computing problem is a language, a yes set, and for all inputs, you have to decide whether or not that input is in the language or not. Okay. So equality is the set of strings which are some number of zeros, let's say n of them, followed by an equal number of ones. That's why we call it equality. Okay. So let's see how a DFA would try to solve this problem. So let's take an input, okay, which is let's say 0, 0, 0, 0, 5 of them, 1, 1, 1, 1, 1, 5 of them. Now you have a DFA. It's got a bunch of states. Okay. And it can move around states as it reads the input one by one. And then when it's done reading the input, it's moved around states. It looks at its current state. If it's a yes state, it says yes. If it's a no state, it says no. Okay. So that's how the DFA works. So let's see how it would work on this input. So, it reads in the first 0, maybe it moves into I've seen 1 0 state, okay? Then it sees the second 0, I've seen a second 0, then a third 0, and so on. So it can use its states as a primitive memory to count how many zeros it's seen. What's the problem? The problem is it has a finite number of states. So it can only remember a finite number of zeros that have passed by. Okay? So the fundamental issue is, a DFA is very good at determining whether or not a 0 has occurred. Okay, because as long as a 0 has not occurred, it's in some reject state, and the moment it sees a 0, boom, it transitions to a 0 has occurred. But it cannot count the number of zeros that have occurred. Okay, so DFA cannot remember the number of zeros. Okay, because it doesn't have enough states, and it in principle will need to remember an arbitrarily large n. It cannot remember n. And that's because it has no scratch paper. No scratch paper. And if you think about it, if you're doing complex math, you don't do it all in your head. You have, scratch paper for intermediate derivations and things like that. Okay. So, your CPU is the brain. It's like the DFA, and you have scratch paper. That's what allows you to do such complicated stuff. The DFA has no external memory. Okay. And so one way to allow it to maybe solve this problem is to give it an additional capability, improve the model, okay? Build a more complex, a superior model. Okay, so we could give it additional capabilities, i.e., for example, an external memory. So give the DFA an external memory. Okay, and the kind of memory that, let's talk about the most primitive memory that's easy to mechanically implement, okay, is what we call a stack. So literally think of a stack of papers. Okay, so a stack memory. Okay, and the reason this is easy to implement because I'm only going to give the DFA access to the top of the stack. Okay, so whatever's on the top. So think of a top access only memory. Okay, so you can access the top in a stack. Okay, and you can access means you can see. Okay, you can write to the top, so you can push something on. You can push, or you can remove whatever's on the top, so you can pop. But you don't get access to what's going on inside the stack. So you can only see, and all the action is taking place on the top of the stack. So no access to inside the stack. So this is a relatively easy memory to sort of implement because I only need to give you access to the top. But let's see how this primitive memory, this stack memory, this top access only memory can help the DFA to solve the problem 0 to the n, 1 to the n. 0 is followed by an equal number of 1s. Here's what it does. It starts in a state of I'm expecting zeros. So I'm going to be reading in zeros, and every 0 I read in, I'm going to push it onto the stack. So 0, 0, 0, 0, 0. I push, which is fine because all I need is access to the top of the stack to keep pushing a 0 onto the stack. Now, the moment I see a 1, I say, it's time for me to start popping from the stack. How do I sort of implement that in the DFA? I change states into a new state which says popping from the stack. So every time I see a 1, I now pop. I can only pop from the top, but that's fine. I pop, then I pop, then I pop, then I pop, then I pop. Okay. And at the end of the string, I check the stack. If it's empty, I say yes, all my operations succeeded. If anywhere during this process some error occurs, I immediately know the string is not in my language and I reject. So we see how a very primitive stack memory allows the DFA to solve this problem. Okay. Now, we won't spend too much time on stack memory because we have bigger fish to fry. But one reason to mention this stack memory, before discussing context-free languages, because it turns out that context-free grammars / context-free languages are very related to, problems that can be solved by DFAs with this primitive stack memory. Such a DFA is called a push-down automaton. To be absolutely technically correct, we would call this a deterministic push-down automaton because it's a deterministic machine, deterministic finite automaton with a stack memory. This is called a deterministic push-down automaton. It's related to what we're going to talk about today, but we won't explore that in that much detail because we have big fish to fry and only limited time. Okay, so let's erase, come back and talk about context-free languages, parsing, compilers, all that good stuff.